Okay, we have here the Laoss GUI, and just for your information, there is this. That's how it looks when you open Laoss, and then in the help dialog, you see there's a link to the Laoss manual and Laoss tutorial. And in the Laoss tutorial, we have a document where we have several examples explained. There are about 8 examples. We don't do the design of geometry with LibreCAD because that's actually only needed for very special geometries. Otherwise, we can just start with parameterized geometries. So that's the tutorial. And if we just start step by step here in the graphic user interface, we first are here in the project path. So we have to. I have to select new project first, and then we can select here a geometry. For instance, a rectangle with metal stripes, or these stripes are rectangular. Let's choose the rectangular one. And you see here, we select the units, and geometry here we could say 10 by 10, but maybe instead of meters, we should select millimeters. And then we already see, if we press the Show Geometry button, then you see the geometry on the right-hand side. And then you can, in this example, because it's a rectangular grid, we can select the number of metal lines. In horizontal direction, there's 1. The number of cells in vertical direction is 2. But if we increase to 4, press Show Geometry button again, we get 4 cells. We can also increase the number of cells in horizontal direction, and then we get just directly a preview of the geometry. That's the choice of geometry, first step. And if we also want to preview the mesh that will be generated, we can go here and just define some minimum and maximum element size. And we actually have 2 meshing algorithms implemented here, but let's see. If we have a 10 by 10 millimeter domain size, the minimum edge size we could, for instance, select 0.5. Maximum elements edge size is maybe 2. And we can make a quick preview. Now our min-max are very coarse, so we have very coarse mesh. And then the idea is, okay, maybe it's better to make a smaller element size, and we can just decrease and rerun, enter. Wie much so? 0.5 we will select as the maximum size, and then you realize, now it's looking more reasonable size, but maybe we can even limit more and decrease this to 0.2, and now it's even more reasonable, and we get a preview of the number of edges or vertices in the mesh, the number of finite elements, 7,000, and just keep in mind the number of elements and vertices will determine your calculation time. If the finer the mesh is, the more time required. Down here we also have the option to select the mesh refinement, 1 iteration of refinement or more, but we can just select 1 maybe. Then the second step in the second tab here is the JV local coupling law. For simplicity, we can just simulate 1 single electrode instead of coupled. then we have to enter less parameters in this live demo. And you see here that we would have the option to activate thermal modeling, but for this first example we do not. And then we can select here the default domain, and the metals are separated here. Maybe I should for my mouse cursor is maybe better. Right. And for each selection, so if we have the electrode selected here, we need to go down to the electric coupling and select JV law. For instance, now this is Ohm's law is, as you know, just conductivity and the thickness to generate the JV curve. But instead, let me just import the JV curve from the folder. There are some examples of in the example folder, I think. So in the tutorial examples, there are also some JV curves measured, which are used in the tutorial examples. And here we want to go into the installation directory, I think, where the Laoss software is installed. And inside the Laoss folder, there is an example folder, and there are a selection of JV curves. So typical OLED JV curve, the first one maybe, we can open and visualize it. Don't forget to press the apply button. So we have to apply this JV law to the selected subdomain. We have effect. Current efficiency needs to be 1 here, maybe. So this is the imported JV law. If you press the axis, the logarithm y-axis, und jetzt kannst du rauszoomen mit dem Ding, oder? Ich hatte den noch nicht erkannt. That's the logarithmic JV law that we imported for the default area. And if we want the OLED to be uniform, the coupling law must also be selected below the metal finger. So we need to just select the same coupling law for the Okay, and so now the electrical coupling has been selected. When importing a file, you can always enter the units, or you should check that you have the right units, voltage and current density. If it's a JVL curve, you can also enter the unit of the luminance column in the ASCII file that you import. And then we can go to the next step, which is the electrode definition, meaning we need to select the conductivities, electrical conductivities of the two domains. Now we have metal and electrode domain. Here we can enter a bigger number for the default domain and a smaller number for the metal property to show that the metal is more conductive than the area between the metals. Yes, like this, 10 ohm square for the default area and metal 1 ohm square. And then we can go to the boundary conditions. We have so-called edges 1, 2, 3, 4, which are the outermost boundary, the sides of the square. You see there is an indicator. If you select on the left, you see the red line shown on the right. And for each of them, now we, instead of current density, we choose voltage. That's typical to apply voltage, but there's a choice also to prescribe a current density. But let's choose the voltage, just same. Can you choose 6 volts? Because then we are above the turn-on voltage of the JV curve to have a lot of current. If you select voltage below turn-on, you would have very little current and less resistive losses. So enter, for each edge on the side, enter 6 volts, for instance. And with these 4 steps, defining geometry meshing, defining coupling law, defining the electrode conductivities, and then the boundary condition, these 4 steps, that's sufficient to run a simulation. So now we can, or should be sufficient, let's hope. Yes, so Roman pressed the run button, and we get a log window, just some information, some runtime information, and then the final result. So in 5 seconds, we have a distribution of potential shown on the right-hand side, and on the left, there is a navigation window where you see all the different outputs, potential in the top electrode, source current density. That's the second result. Basically, that represents the current density flowing vertically through the semiconductor stack, but this current is then going into the lateral electrode, so it looks very similar because no current is lost. And the potential. You see some more outputs like the ohmic losses in the top electrode. So that's interesting here. What we have plotted here is the power density. So it's watts per square meter. Because the metal lines are highly conductive, they will collect the current, and then there's a higher current density inside the metal line rather than between the metal lines, which is visualized here. And to double check if there's a show edges on the upper right, allows you to show the numerical mesh, and usually the numerical mesh also follows the geometry, so you can kind of double check, is this consistent with the geometry that you have chosen? And there's possibility to have a different representation. Instead of potential, you can also look at the gradient. On the right-hand side, one can choose electric field, or either as a scalar quantity, electric density, or contour lines. There's another representation. So there are different ways to visualize this FEM result. And also lines or arrows to visualize this field as a potential gradient. So by zooming in and out, you can investigate the distributions. And then global values per subdomain, that's also usually interesting to check, because the previous current density, okay, that was position dependent, but the subdomains allow you, for instance, for the OLED pixel problem there, RGB, you could then, the software would measure or determine the current flowing through each subdomain. Here we only have 2 subdomains, the main electrode, the large electrode, and the metal grid placed on top. And and the metal wood, okay. So far, and finally there's also a flux per boundary condition, is more numerical information, how much current is flowing through the edge. So if you apply a Dirichlet boundary condition for the potential, you will end up getting the current density flowing through that boundary condition. And now, I hope, did everyone get such a kind of example? managed to get some colorful map image of the potential distribution. So that's 5 seconds for 1 voltage. And now let's try to make a voltage sweep, vary the voltage. That's simply done in this dialog, in this tab, where you have to enable the sweep. Press the enable button, and then now we just make 1 sweep, but you could even nest a sweep, have multiple sweeps nested. But here we select to vary the potential at this quadratic boundary. And the pop-up window lets you select whether all 4 sides are connected to the same potential. Yes, we want to connect it to the same potential. And we sweep the applied voltage from 0 to 10 volts in small half-volt steps. And in the end, it's the unit given there. Yeah. And now we can run the simulation, and again we see the log window showing progress. And the tolerance number that you see in the output, I think that's the R, the residuum. Yes. The residuum that I mentioned in the method explanation. Oh, that's kind of the accuracy of simulation that you can prescribe, that you can require. So 10 to the minus 7 for the residuum value was chosen here, or as a default. Was hat viel Step? 17, okay. And now the total device current diagram, that's an evaluation of the total current flowing through all boundary conditions, or we have, right? Or one, or is this the integral of the total current flowing between bottom and top electrode? It's the integral of the current density. So the unit is current in amperes, not divided by area. But now you see it still resembles the JV curve that we had imported. And now it's possible to compare this, select their plot and import the JV curves with the right pop-up window, with a mouse pop-up. And then we can go to graph, and visualize the input JV curve together, So they look very similar, very identical, meaning that there is little or no lateral voltage drops happening because we have added these metal grid lines. So in this case, it's not so impressive because the conductivity is very high. The metal grid lines support the conductivity in the electrode. But otherwise, if we would leave away the metal grid, if we would reduce the number of metal grid lines, then the current density curve would shift to the right. You have question for this first exercise? Did you manage to reproduce this kind of exercise? Maybe now that we have an example of OLED and electrical modeling, let us open the pixel crosstalk. Pixel crosstalk is an example where physically very similar to what we have shown here for the simple OLED, but in a pixel array, we have a few more domains. So for each R, G, and B pixel, we need to select the JV law. This is the simulation domain. So 6 blue pixels are shown here. This drawing was made in a CAD software, I think, and then imported as a DXF file. And the mesh, if you scroll down, you can maybe visualize the mesh. Run meshing. Yeah. That's the mesh that was used here. And looking at the JV input laws, you see here that that these subdomains, this is the area between the pixels, that's the default area, and then we have 3 pixel areas, blue, green, and red, which are visualized on the right-hand side. And for each of these pixels, we have defined the import JV law. It turns out so that you see here from the list that the electrical properties between the pixels is only a lateral conductivity. There is no assumption about a vertical JV law in the area between the pixels. So that would be an addition, a different assumption. I mean, it really depends how the OLED display is fabricated. If there are more layers, it could be also that there is vertical current flowing between the pixels, but that we neglected in this case. And here's the visualization of these JV coupling laws. So this kind of JV laws, current density versus voltage, must be determined separately, either by measurement of a single pixel, very small isolated pixel, or by simulation. It's a bit funny that we see a kink here in the JV law at low voltage. Don't get confused about the X scale, the voltage axis here. Yeah. Yeah. And then the electrodes, maybe you can show the Dirichlet boundary condition of the blue pixel. Where is the voltage applied? You see here that the pixel, the subdomains have, I mean, the blue pixels are these rectangles, and in the software we can apply the 6 volt, for instance, or the applied voltage at the boundary of this rectangle. And all the other pixels have a potential of 0 on the anode. Okay, and then maybe we can run one simulation, or actually it's already a sweep, I hope. If it's which is long, oder? Weiß nicht. Maybe the if we choose a step voltage of 1 volt, then we have a faster result. One could also increase the mesh size, so we have less degrees of freedom to accelerate. Oh, now it's finished already, I guess. Now Roman is selecting the different subdomains, R, G, and B, and plotting the JV curves together in one diagram. Yeah, logarithmic current versus applied voltage. The red curve here, that is the blue pixel where we apply the voltage, and the other 2 curves are the neighboring pixels where you see there is significant parasitic current flowing into the neighboring pixels. And that's basically the example of that we based our own simulation study on, and that we published in a paper. Maybe, yes, I think I've presented it in the presentation. Okay, anyone interested in solar cells? I'm not sure where is the, yes, solar cell example. Can you open a tutorial example about solar cells? Maybe, which one is the metal finger, the metal grid variation, or? I don't, OPV. There is a tutorial example which sweeps the metal finger, no? Optimization, yes. That was an example that I had in the presentation. So Roman opened a session that has already stored results, is that right? But if you would, whenever you close a project, you can keep the results are still in the folder. And in this particular example, you see that the power, what is this? The power?
Maximum power diagram in function of the metal finger width.
Okay, so there is some built-in post-processing that the raw data, the JV curve that is simulated, is evaluated for maximum power. So the maximum power point can then be visualized versus the sweep variable. And in this case, the sweep variable was the width of the finger. And this, but now it's confusing that the power is negative, or so, right? So now it delivers power, it's negative. So the optimum is the minimum there in the curve. So it's a similar representation as in my presentation. But if you, I think this example is in the tutorial, you could open it there and let it run on your computer, that you would get the same, right? You would get the same example. And on the left, you see the navigation. When you do a sweep, you can still, for each applied voltage, you can still visualize how was the potential distribution. So you can, for instance, maybe you can show two examples where we recognize the different thickness of the finger width. Here the finger was quite small, and the last one was the thickest, maybe, yeah. Or yeah. But if you electric intensity, then you see the peak. Yeah, that's the thickest value of the finger width in this example. So it's easy to do systematic sweep of parameters, not only geometry but also material parameters. You can vary the. If you show the sweep dialog, there's a pull-down menu. In the view, yeah. Here you see a big choice of what can you vary. You can vary boundary conditions, the potential temperature, and so on. Electrode geometry, that would be is that the total size of the, for this particular total size of the simulated domain, and the finger parameters. And the electrode parameters, we can vary the sheet resistance values. And in the coupling laws, this is only possible to sweep if it's an analytical law. So for Mott-Gurney law or Ohms law, we can select analytical model parameters to sweep. And thermocoupling, that's the next topic in the presentation. Yeah. Yeah. Okay. Thank you for this demo.